IGS and STP files. And these are all the different geometry files are supported by different softwares which are under ESI suite, under ESI multi-physics suite. So if you see, Visual CEM is the software which is actually completely dealing with the antenna designing part. So this is the environment of Visual CEM. Let us just open Visual CEM and have a look at it. So this is what is the window, what we'll be getting it. Here at the left top, you'll be actually getting an application window. Here you can see process executive, mesh, CEM, and viewer. So mesh is the initial window where you'll be doing your CAD creation, import, repair, etc. And also for mesh assignment also. Similarly for CEM, all the properties assignment. Viewer for results. So whenever you're trying to import some CAD, you can also go through CAD operations as well. So you can go with CAD options like this. You can select mesh and you can go for CAD options. You can see the CAD options also. If you're trying to import something, import some structure from other two, in terms of IGEP, you can import it and you can go ahead with this tolerance scheme mechanism. So we have stitch tolerance and the other things readily available. So these are the CAD options which are readily available. So coming to the presentation. So these are the things what we have to remember whenever you're going with a mouse. So in mouse, if you want to rotate your complete design, you can drop down the design and you can actually rotate it. And similarly, if you want to roll the design, roll center, I mean, you can go with mouse wheel where you can zoom in and zoom out. Similarly, for panning, it's nothing but if you want to move the particular design from left to right, you can do that. I'll show you once we have opened the design, I'll show you these things. But as of now, for rotation, you have to hold your mouse button and then rotate it. For zooming, you have to zoom in and zoom out. You have to go with scroll option. And for panning, you have to right click, hold your right click, and then drag it across in order to move the design. So especially in CEM1 software, in Visual CEM, we actually have n number of shortcuts to be remembered. So while we are exploring each and everything, we'll come across different type of shortcut keys and the other things as well. So you can see we can select the left mouse, so you can select the surfaces. So we'll come across this particular thing of going with horn antenna. I'll show you how exactly we'll be selecting the design. I mean, we have to select the parts actually. So I'll show you how exactly we'll be selecting that as well. And this is complete your visual mesh. Whenever you open your mesh, this is the window what we'll be getting it. So if you just click on new file, this is the window what we'll be getting it. This is the framing. Whether you want to see a wireframe of your structure or you want to see a complete flat frame or you want to see a boundary box, all these things are available. And operations, whether you want to do curve operations, surface operations, volume operations, and node operations. Similarly, meshing, what kind of meshing you want to go with, either 1D meshing or 2D meshing, etc. And similarly, checks. Checks is nothing but it's an option where you can check your element normals, how exactly your antenna will radiate and which direction your elements are radiating. All those things we can check it out. So views, these are the views window, whatever we have visualized. So wireframe, how exactly, solid model, if you want to go with, you can do. And if you want to go with split model, you can go with this, etc. And then utility, utility box is for text editor. If you want to do some measurements, etc., we can go with that. And mesh visibility, we can also set the options for mesh visibility as well. And a visibility for the structure. And CAD. CAD is nothing but your computer-aided drawing. So it covers up the points, curves, surfaces, etc. Parts will be which will be available separately. Parts and whatever window you can see at the left-hand side under .vdb. This is nothing but your final window. So under this window, we'll be actually getting your CAD. We'll be actually getting your frequency, excitation, what kind of solver you're using that, and what is the output parameter you're setting up. Similarly, how many surfaces you're setting up. Similarly, what is the mesh size you're setting up. All those things will be readily available in this particular window. Coming to parts. So if you are designing an import, if you're importing a design from a tool, from a CAD tool, any other CAD tool, and you have imported in IGS, basically you will not get everything in terms of materials. You have to bifurcate all the materials together, and then you have to get started with the new implementation. So parts should be selected. Once we are getting through the particular designs, we'll come across these things as well. And this is nothing but your part manager. If you click on F11, you can see the complete part manager list where you can see the complete parts. How many parts, how many surfaces you have, how many curves it has, how many orthogonal positions it has, all those things will be readily available. And how many elements does it cover also, that information is readily available. And then menus, file menu, in order to save your project, open your new project, edit. Editing options, if you want to do some editing options, you can do that. And viewing, display and view options. Similarly, curve is for creating and editing curves. Surface is for creating and editing surfaces. And then volume is for volume. And then node operations, if I want to create some nodes on the design, I can go ahead with. And 1D, 2D, 3D are for creating the mesh, respectively for the structure, whatever you're using. Okay. Coming to menus, so check menus is for checking your quality of the mesh. So with what quality you're going with the mesh and how exactly your normals are located with, all those things we can actually look at about. So this is the complete information of the Explorer window, what it has in the mesh. Not only in the mesh, in all the windows, you'll be having the same information like parts, nodes, elements, materials, mediums, group, boundary conditions, loads, probes, ports, spherical wave setup, general far field, monostatic near field, etc. The different type of parameters will be readily available. So we'll come across all the parameters, we'll understand the importance of each and every parameter. And then in visual viewer, we'll be actually having 3D plots and 2D plots also. We can plot up 3D and 2D. We'll go ahead with that. We'll see the example. And this is nothing but your importing of the CAD. Once you import it, we have some options in the import. As I've already showed you this particular CAD options, we can import the CAD with the stitch tolerance also. You can manually do that, or else automatically you can do that. If you're getting some issues with the automatic detection, then you can go for the manual stitching as well. And then once you import it, you'll be getting a log beneath your, once you import a design, what happens is you'll be actually getting a console log. So in this log, you'll be getting the information whether you're going with a proper procedure or you have some errors in the design. All those things we can visualize. And similarly, edges with the connectivity is equal to 1 is thick red. So we'll be getting some thick red, some few adjustments has to be done on the design part. So we can go ahead with repair option, which is readily available in ESI 7. So whenever you're going for some export, if you want to go for surface repair, you can go for repair option where you can click on check. So that is what has been mentioned in the particular presentation. So as long as you get no problems identified, it's fine. So if you get no problems identified, autocorrect all is also an option where it tries to correct it. So if you are getting some misshape, I mean, if you're getting some wrong shapes out of it in the auto correction, then you have to go for tolerance adjustment and then you have to reshape it once again. Once you got the no problems thing, then you can go ahead with the implementation part. So in options also, we have autofill gap and create surface. For example, if you are getting some gaps in the surface, we have to either go for autofill or we have to go for create surface at that particular location. Okay, select source edge, select target and apply, click on accept so that it will be connected. And then click on the second surface, accept, delete the internal edge. So the complete air gap will be removed and then you'll be getting a proper connections. Similarly, stitching. So if there is any stitching issue, like the complete single layer has been stitched into 2 parts, I mean, bifurcated into 2 parts, you can go for stitch as well. So these are the additional options what we have under repair. So if you are importing a design from the other CAD tools, you can import it, and then you have to go for problem identification. Either you can go for manual correction or auto correction is also available. So we can identify and correct it. We can go for CAD repair for the unclassified problems also. So we have to see what exactly is the design is all about, how exactly you can correct it. So that's one major thing what we need to have. Sometimes you will be getting this kind of issues. So you can delete the surfaces and then auto fill the gap so that you'll be getting a auto filled gap with the proper matching. So these kind of corrections we need to do. So individual meshings is also possible. For example, the meshings could be done on the individual structures as well. For example, if you're dividing your complete problem into subparts, if you are going with horn antenna, outer surface, inner surface, and again port, if you are dividing into subparts, allocate different type of meshings for different structures. So here also you can divide the model into ports, different parts, and then you can excite it. So you can see we have a port, we have antenna, and then we have a UAV structure or else a jet structure what we have. So UAVs will be kept on the front, and backside you'll be having a port excitation. So we have to create new parts. This procedure also you'll understand how exactly we are doing that. Once we are going with the advanced example, we'll be coming across with that particular part as well. And then ports. So you can create a part for the ports as well. And then you have to go for the excitation, how exactly you want to go about. So front side of the antenna, back side of the antenna, front port and the back port. You have to split up the things. So once you're done with that, you can go with auto mesh where you will get for all the dimensions, or else you can separately do the meshing for the antennas also. Antennas and ports, whatever you have, you can do the separate meshing for these particular designs. So this is local refinement. So based on your particular frequency, we'll be actually assigning the mesh size. So this one type of calculations what we have to do, which will come across when we are trying to do ahead with horn antenna especially. So here you can see two edge groups we have. One is of 2 and other one is n. So sex group is 2 in a sense. This is what is a main port excitation, which actually excites your inverted F antenna. That's the reason I'm making that part far more precise when compared to the other parts. Why exactly? If you are going for the optimal mesh, like if you are going for the minimal size of mesh, what happens is the level of accuracy with which you are getting the solution will be increased. So this is one thing. And here you can also split up the mesh, as I've said. So topo mesh is one of the option where you can go for different type of meshing styles. So you can remesh a particular part and you can see it, how exactly it is responding. And then mesh quality and check and mesh repairs. So mesh quality check, you can go for coincident nodes check, whether you have any coincident nodes, like check for the coincident nodes. If they are detected, they can be fused together. Similarly, coincident elements as well. And element normals, how exactly your element normals are coming out. So this is one of the major part when you're going with some antennas, like especially when you're going for the port excitation antennas, always you have to observe your element normals. And then surface mesh, check surface mesh is nothing but checking the quality of your mesh. Okay, this one is nothing but checking the surface mesh, check the boundaries, cracks in the surface and the quality of the particular mesh. Similarly, some corrections what we can do on the meshing part. So this is completely related to the visual mesh. Under visual CEM, as I've told you, we have different parts to be contributed. Boundary condition like PEC, PMC, IBC, etc. Different type of boundary conditions, whatever you want to project, you can go ahead with that. Materials, here we have a material set which is readily available. So even though the material is not available, you can also go with a parameter change also. Like you can calculate the epsilon and mu of that particular material, and you can enter those material and you can type the material name. So based on which the equivalent substitutions will be done and you'll be getting a proper response of the material. Similarly, mediums, exterior medium. So exterior medium is in the sense, whatever antenna you're creating, you have to create an exterior medium around it. It's like you're creating an air boundary around it in order to assign the ports, in order to assign the sources, etc. Different type of things. Grouping option is for domains. This is for MDMM. Once we come across the MDMM simulations, we'll try to look at this. Similarly, loads are the different properties. Like if you want to put some load like serial RLC, parallel RLC, general conditions, you can go ahead with that. And assigned loads, if you want to put some load based on your own condition on the wire or on the edge or on the list of edges, you can go ahead with that. Probes is nothing but, for example, inside your antenna, if you have an additional structure where you want to probe it, I mean, you're inputting your port excitation, you also have something called as probe. So for those kind of probes, we'll be actually assigning this probe and general properties. Ports is nothing but creation of ports and definition of ports. If you want to go for port excitations like TE10, TE11, TM11, so different type of port excitations, if you want to go with, you can go ahead with a port excitation. Similarly, spherical wave expansion setup. This is an advanced concept which I'll be dealing with once we are coming across this particular topic. We'll be dealing with the spherical wave expansion. Far field setup. So far field setup, we have to set up a far field around your antenna. This is very important. So once you set up the far field around your antenna, you can see the coverage of the antenna throughout your far field. Throughout your far field, how exactly you're getting the response and all those stuff, you can actually observe. Monostatic near field, if you want to go for near field computations, you can go ahead. Similarly, excitations, sources. So we have different type of excitations and sources. We have plane wave excitation. So this plane wave excitation will be useful whenever you're going for RCS calculations on the UAVs, etc. Delta gap will be actually useful if you're going for monopole or if you're going for dipole antennas, etc. Similarly, dipole, there is a special property, dipole. Similarly, spherical wave expansion. If you want to, instead of importing your antenna into a structure, if you want to put your antenna source there, you can actually make use of spherical wave expansion. Once we come across this particular concept, we'll really understand it. Similarly, line source, if you're going with line feed of source, you can go with line source. And general field of distributions, this is for higher end solver. If you're using, you can go with this. Plane wave sequence, this is also for UAV, the RCS computations. Multiple sources, if you're going with multiple sources on the same thing, you can go with that as well. Similarly, plane wave, how exactly you have to excite your plane wave in real terms of theta and real terms of imaginary terms of theta, real terms of phi, imaginary terms of phi, and delta gap. Delta gap in the sense, it's nothing but either you will be projecting, you'll be giving a characteristic impedance of 50 ohms. So with 50 ohms proper impedance matching, you'll be exciting your antenna, and then your antenna will start exciting, and you'll be getting a pattern around you. So you have to put your characteristic impedance and you have to assign a node. So you have to assign a node for this, whichever node you want to assign, that particular node if you select, then we can excite it. Similarly, dipole in the sense, it's a menu for creation of dipole source. If you want to create a dipole source directly, you can go ahead. Why exactly this kind of things will be required is if you want to analyze a radome structure. I mean, if you want to put a radome and you want to put a dipole inside it, you want to analyze how exactly it is performing, you can go ahead with this kind of things. And spherical wave expansion. So this is nothing but you can actually replace your antenna with a .swe file, and you can place .swe file into your particular structure, whatever you want to analyze. Similarly, line source feed, whatever you want to go with, line voltage source. General field distributions. So it's completely related to the field, electrical and current field distributions, what we have. Plane wave sequences. So plane wave sequence, this is also for UAV structure if you want to analyze. So first angle of theta, last angle of theta, steps of thetas, phi first angle, phi last angle, and steps of phi's. All those things we can analyze. Coming to multiple source, so this multiple source is a window where you can actually assign all the types of sources what you have done so far. And then similarly, if you want to go for array computations, there is an option in Visual CEM where we can go for array computations as well. So post computation for the array, whenever you're setting up the array, you have to go for post computation results as well. Coming to output parameters, we may get different type of output parameters like frequency, final output, length, unit, time convention, based on the solvers what actually you're using. Coming to frequency, you can assign the frequency in terms of single point of frequency or a multiple intervals of frequencies also you can assign it. And this is the output menu, how you'll actually configure. For example, if I'm giving a delta source, I can configure all these things like input power I can calculate, input impedance I can calculate, reflection factor, SVWR, something about VSWR we can calculate. So these things we can compute. And apart from you have to set the length in terms of units also. So modeling unit, if you are putting in mm, you have to go with mm itself. And then solver settings. So these are the solver window where you can actually assign the different type of solvers like MOM, multipole solver, FEM solver, MOM PO solver, MLFMM PO solver, and PO solver. Different type of solvers what we have. And then solver path. So you have to set up the solver path as well. And RCS calculations, you can go with RCS calculations. Job manager is nothing but it's available in a CEM window where you can completely run your design and you can get the results of your own design. Coming to visual viewer, we can plot up the 3D plots like surface currents, magnetic fields, electric fields on the far fields and near fields, etc. So if you go with horn antenna, you can see the field currents like this, and even the response of your horn antenna also, far field response. So this is a 3D animation. So you can also go with some animation control as well, where you can see the excitations, field lines, etc. 2D plots, like you can visualize your 2D plots also, like frequency versus gain plot, etc. Like return loss also you can calculate. And this is your polar plot, what you're plotting up with a dB10 as an axis. And this is E field setting phi to 0 and plotting up. So this is how actually we'll be getting the different type of results. If you want to go ahead with S11, that is nothing but for your return loss, you can go ahead with that. So this is the return loss what we have. So Z in the sense, it's nothing but your input impedance. You can also compute your input impedance as well. So real and imaginary parts together will be getting it. So this is what is a brief intro, what I would like to share with you on three different domains what we have. So once we get started with the design part, we'll come across each and everything. So now let us just switch back to the original thing.
Rohit sir, just 1 minute.
Yes, sir.
Yeah, I think all the students are presenter because of the region. Might be you are going to show your screen, correct, during the design?
Yes, sir.
You should not remove the student in the midway. If attendee, then will be problems because you cannot show your screen during your design. Okay, so you just
okay. Fine, sir, understood. So I should say in one domain itself. I shouldn't switch up.
No, I think a student, they are removing 1 or 2 students.
I didn't get you, sir. Students are removed?
No, I think they are presenter. Everyone is a presenter.
Oh,
option is there. So might be they are removing 1 or 2 students.
Okay, let me change that, sir. Like, give me just 1 minute. I will make.
Yeah, during design will be fine, sir. I think time.
Yeah.
I think will be good if you have attendee only.
Yeah. So, Rohit, please continue with the meeting. I'll take care.
Yes.
Yeah. Thank you, sir. Thank you, sir.
Yeah. No.
Thank you, sir.
Yeah. So coming to today, we'll just get started with the frequency domain solvers. So I'll cover up until frequency domain solvers only. So coming to frequency domain solvers, what we have in ESI SEM software like Visual CEM is MOM. MOM in the sense it's method of moments, and MLFMM it's multi-level fast multipole methodology, And then we have physical optics, which is for high frequency solving. Or if you're going for a complex problem, you can go with that. FEM, it's a nominal method which